In warm-up 2, we are going to talk about how to draw a representation of something that is a 3D graph on a two-dimensional surface. And there's a little bit of an art to it. So we'll work on that. But I did want to show you first what what we'll be doing. And so here you can see an example of a 3D plane. So a 3D plane really is just what would have been like an XY plane, but then they made that be kind of like the horizontal piece of it, and then they have a z-axis popping out, and that z-axis is perpendicular to both the x-axis and the y-axis. So the z-axis is perpendicular to the xy plane. So hopefully that makes sense. And so I'm just kind of playing around with the perspective here just a little bit, okay? So if I was to say plot the point that we had, let me fix the perspective here just a little bit. How do I want it to look? Maybe about like that. There we go. If I wanted to plot the point that we had from the answer for the last problem, so what was the answer for warm-up 1? It was 2. So really quick, I'm going to back up. You could see the point starts at the origin. And in a 3D system, the coordinates of the origin would be 0, 0, 0, because it lines up with 0 on the x-axis, 0 on the y-axis, and 0 on the z-axis. Now, over here on the left, I'm going to increase the x value to equal 2, simply because that was the x coordinate of the point of our solution from warm-up 1. And so now the point is at 2. It lines up with 2 on the x-axis, still lines up with 0 on the y-axis, and it lines up with 0 on the z-axis. So this would be the point 2, 0, 0. Now I'm going to change the y-coordinate to be 3. And so notice, I'm going to change the perspective here. Notice that, this is just good old-fashioned lining up with 2 on the x-axis and 3 on the y-axis. But because I haven't moved vertically at all, I haven't moved in the z direction at all, this point now would have coordinates 2, 3, 0. Well, now if I was to increase the z coordinate, let's say I increase it to be 5, simply because that was the answer to the last problem. Now this point has coordinates 2, 3, 5. And I hope it makes sense that when you graph something in 3D space on a two-dimensional surface, you have to show this path here as to how you got there. Otherwise, depending on your perspective, it could look like it's just about anywhere. I hope that makes sense. Anyway. Okay, so there you go. So in the next little segment here, we'll talk about how to draw something that represents 3D space, but just on a two-dimensional surface, like your paper. All right, my friends, let's get started on trying to draw something that represents a 3D coordinate plane, but drawing it on your paper, which is two-dimensional. So it's just all about creating an optical illusion. So getting started, so go ahead and take your straight edge, and we're going to go ahead and draw that z-axis first. Now when you do this, we're going to kind of create an optical illusion here. So I'm going to have this be the origin, which would be the point 0, 0, 0, like we mentioned before. And then the positive z-axis would go up from there, and the negative z-axis would go down. So to create a 3D kind of look to something that's two-dimensional, what we typically do is we make the positive side of any given axis, we make that be solid, a solid line. And then we make anything that represents a negative axis be dashed. And again, it's just to create an optical illusion. It's not because you have to, but it really does help to kind of like have things show up. And then also, again, just to create an optical illusion, we typically only put an arrow on the positive side of the axis. It's not that it doesn't go forever in the negative direction. It's just because, again, you're trying to kind of like make the positive axes pop and kind of look like they're coming out towards you. And then the lighter stuff, make it look kind of like it's going away from you. So this is the z-axis. Okay, we'll add tick marks last. And then you can choose different perspectives, but I'm going to go ahead and choose a perspective where the Z and the Y axis, we're kind of like looking at the ZY plane head on. And so for that purpose, I'm going to go ahead and let the right angle show here. So go ahead and create a right angle. And then to the right of the origin would be the positive Y axis. So make that solid. And then to the left would be the negative Y axis. So go ahead and make that dashed. Again, arrow on the positive axis side, and then the label also. The labels are more important than ever because there's such thing as a right-handed system and a left-handed system, and the labels would let you know kind of which one you're using. So, okay. Anyway, and then to create kind of, so then we're going to have the x-axis kind of like coming out toward us. And so go ahead and put your, I don't know, I guess I create what looks like almost like a 30-degree angle between the z-axis and my straight edge. And then the positive x-axis is going to come out toward us. Like this, and then the negative x-axis would be going away from us. Okay, and then right now, let's label that. Right now it might not be super obvious that the positive axes are coming toward us and the negative axes are going away from us, but we could add tick marks to like add to the optical illusion. So when you put tick marks on the z-axis, you're making them look like they're perpendicular to where the xy plane would be. So it's pretty straightforward. You just draw it like this. Just do your best to make them look evenly spaced. You could also use your straight edge. We're going to take more care on this first graph than we would on any other one. After this, we, don't make them quite as neat. And then let's do the tick marks on the y-axis next. So same thing, the tick marks on the y-axis should appear to be perpendicular to the xz plane. And so actually, that would look like this. Yeah, so that would be, make sure that when you do these tick marks, you've got them so they look like they're parallel to the x-axis. It should help with the optical illusion. Like so. Okay, and then the tick marks on the x-axis should be parallel to the YZ plane, and so if you just try to make them be parallel to the y-axis, it should accomplish that. So that would be like, again, we'll take more care with this graph than we would with any other one. And then if the 3D look is not, this isn't really popping and looking like the positive axes are coming towards you and the negative ones are going away, you could always go over the positive axes and make them like a little more bold, and that can help with making this look like it's got parts that are coming out towards you and parts that are going away from you. Okay, and hopefully at this point you can see what I'm looking for. So anyway, so we've got ourselves the nicest XYZ plane that we'll probably draw in a long time. And so now what I'd like for us to do, now that you have this 3D plane, is I'd like for us to practice plotting like at least one point in 3D space. And the point that I'd like for us to practice plotting is going to be the point 2, 3, 5. It's, if you remember, it's the solution to that system of equations that we solved in warm-up number 1. Oh, by the way, this is warm-up number 2, is to plot this point in 3D space. So, okay, so with that said, let's talk about how to do it. So you could be a total rule follower and just go in order, like do the x coordinate and then the y coordinate and then the z coordinate. Like you could just do that, okay? And so that's what I'll do first. So let me use orange for this. So if we do that, then we would go start at the origin. You would go 2 units in the positive x direction. And then you'd go 3 units in the positive y direction. And so this can be a little tricky. You're going from here, but you're going, this far. So you're going to go 1, 2, 3 units. So, and real quick, I'll just make this in dash, like you're lining up with 3, but like kind of at that angle because of the perspective. So now I'm at the point 2, 3, 0, and then to get to 2, 3, 5, I need to go up 5 units, but from here. And so I'm going basically 1, 2, 3, 4, 5. I'm going that far, but from here, if that makes sense. So 1, 2, 3, 4, 5. So my path, I'll make it a little bit more bold. I went 2 that direction, then I went 3 along the y-axis, and then I went up 5 units from there. So let me just measure and see if I actually got that last part right. So 1, 2, 3, 4, 5. That would be about like that. Okay, a little farther. There we go. Okay, so that is one way to get to the point 2, 3, 5. Okay. But we're going to show the different paths that you could take to get to the point 2, 3, 5. You didn't have to go x, then y, then z. You could have gone along the y-axis first, and then the x-axis, and then the z-axis. So I'm going to show that path in purple, and you could get to the same place. So start at the origin, and then this time you could go 3 units along the y-axis, like that. And then you could follow the direction of the x-axis, 2 units, and then do the z-coordinate last, and you could get to the same place. All right, now let's use green, and let's show another path. So what's another combination of x, y, and z that we haven't done yet? We could do x, z, y. That's another combination. And so let's do that path. So that would have been x coordinate first, so like this, so now you're here. And then the z coordinate, so that would make you go up 5 from there. And then you go in the y direction, 3 units. And you get to the same place. So 3 different paths for getting to the same place. But there are more paths, right? We could have done this in other ways. Let's see, what else could we have done? We could have done y, z, x. So let's show that. So starting at the origin, going along the y-axis, 3, then follow the z-axis, 5. 1, 2, 3, 4, 5. That one really would line up. And then go in the positive x direction, too. And you can see you have another path to get to the same place. Okay, 4 paths down. How many more do we have? We have 2 more paths, right? Because we haven't done z first. So you could do z, x, y. Let's see. So that would be 5 up. And then 2. And then y. There we go. Okay, that's that path. I'm running out of fun colors. Okay, we'll do red. Okay, and then the last way to get there would have been z, y, x. Okay, so let's do that. Z, y, x. There we go. And we didn't have to show all the paths to get there, or just one of the paths would have done the trick. But I'm hoping that by showing all 6 paths that you could have taken to get to the point 235, it can really help you see that that point, kind of the idea of that point kind of hovering out in 3D space, as if there's a cardboard box with one corner of the box at the origin, and the box has dimensions 2 by 3 by 5, and the point is kind of on this opposite corner of that box. So there you go. And in addition to that, I was hoping that the graphical representation of that point could help people understand why Gaussian elimination, like why it has kind of the format or the flow that it does. So let's look back really quick and talk about, graphically speaking, what was happening with this problem over here. And so, so basically, when you have an equation with what has a relationship between x, y, and z like this, and they're all to the first power, each of these equations represents a plane in 3D space. And so, like, maybe this first equation, maybe that represents like the front side of this box. It doesn't, like, honestly, like, it's more complex. It's like kind of an angled plane, but let's pretend that it represents like this front side of this box, okay? And then let's say that the third row, represents the top of the box. The truth is that it represents a different looking plane in 3D space, but this picture, even though it's kind of simplified, should explain kind of like the geometry behind the algebra. So see how in our work, we, back when we did this problem algebraically, see how we were basically finding the intersection of those two planes. And what did we find? This is a line equation, but this is a line in 3D space. So what we were finding when we found this negative 3x plus 4z equals 14 is we were finding like the equation of this line right here, where essentially the top of the box and the front of the box intersect. So you're just finding where two planes intersect, and the intersection between just two planes would be a line, okay? So then, and I hope it makes sense, like why we needed to involve the third plane, because otherwise you're never going to get it down to that single solution if you really think about this geometrically. So, so let's say the second equation, let's say that is this side of the box, right? And so what did we do with that third equation? We found the intersection between it and the second equation, the second equation that is, and then the third one. So that would have been like the intersection between the green and the blue here. So that would have been like this line right here. And so when we found this back here, that was this, maybe like this line in 3D space. And then when we found this was another line in 3D space. And that's why it's so important that, remember when we chose to eliminate y, that's why it's so important to eliminate y again, because if you don't eliminate the same variable twice, then you'll end up on accident with skew lines. Like you wouldn't get this blue one and this green one where they do intersect. You would end up with something like this blue one and then like this one down here, and they'd never intersect. So that's the geometric explanation as to why once you commit to eliminating, like say y, you're committing to eliminating it again, because otherwise you won't be able to get a point. So then once we had these two lines in 3D space, then we needed to find where those two lines intersected. And that's why it made sense to kind of treat it like its own system of equations and find where those two lines intersect. And then you get a single solution, and then you do your back substitutions and get all of your solutions. So hopefully this picture kind of explains why the flow behind Gaussian elimination is the way it is. So there you go. And it's a pretty picture, so, you know, you can't go wrong with that. All right, my friends, let's take a look at example 1 here. The directions are kind of fun. Solve each system of equations, that's the heart of it, and then write your answer each time in the form of an ordered triple. That's just where you have an x, a y, and a z coordinate. And then in the case where there are infinitely many solutions, we'll make sure that you know how to characterize the solutions in the form of an ordered, in this case triple, in terms of one variable or what's called a free variable. And we'll get to that in a little bit. So spoiler alert, part A here should be a single solution problem where you have three planes and none of them are parallel or anything. And so they all have a distinct point where they intersect. So go ahead and see how it goes. Try to solve this one using Gaussian elimination, and then I'll go through it with you in the next video.